Modeling cubic functions. Our objective, we're going to use Desmos to model data that is best fit by a cubic function. And then we're going to answer questions using the graph and or the model. So Desmos uses this tilde equation to model a cubic or a degree 3 polynomial. Y tilde ax cubed plus bx squared plus cx plus d. Now normally our data will be in a table labeled x1 and y1, and so we would have y1 here and x1 here, here, and here. It depends, of course, on the headings of the table you create in Desmos. Modeling with a cubic function allows for up to 2 changes in direction. We saw that in a previous video, that a cubic function can have up to 2 changes in direction. So, for example, if we were to have a situation, population is increasing and then decreasing and then increasing again, increasing and then decreasing and then increasing again, we could model it with a cubic function. So let's take a look at an example. Excuse me, while I clear my throat there. Okay, example 1. The table below shows the number of millions of older persons in the workforce for the years from 1970 and projected to 2050. And so we have 1970, 80, 90, etc., up to 2050. And we have the population in millions, 3.22 million, 3.05 million, etc., for each of those 10-year increments. Okay, first question. Let me keep my table there visible for you. First question. Let's create a cubic model for these data, where X is the number of years after 1960 and Y is millions of people. Okay, so this is going to be 10 years after 1960. This is going to be 20, 30, 40, 50, 60, 70. Whoops, I didn't mean to write 700. I meant to write 70, 80, and 90. And we want to note here, this is saying to us we want to round our constants, to 3 significant digits. We often round to like the 3rd decimal place or the 4th decimal place or maybe the 2nd decimal place. But if our constant is very, very small, which it is in this case for a couple of our examples, we need to go out further than that, and we can speak to that using significant digits instead of saying round to 6 places. We can say round to 3 significant digits, and we'll see how that's going to look in just a moment here. So in this data, it's going to go into a table, and I'm going to go ahead and I've already done it, so I'll move this. And looks like I've got a light overhead here. Hope we can still see things. Get my Desmos into here. And I've already put the data into the table. 10, 20 through 90 over here, and then 3.22 down to 10.2 in the Y column, the millions of older people in the workforce. And notice my column headings are X1, Y1. And so if we kind of zoom into our points a bit better so we can see them. All right, I'll kind of go like this a little bit. There we go. There's a nice look at it. And you can see we've kind of got actually, it looks like we got a little bit of a turn here, maybe even 2, but we don't really know. We certainly have a bit of a turn down here perhaps, and then kind of going back up. And so it's certainly not a great linear model, and it's not an exponential model by any stretch, and it's not a very good logarithmic model. Let's see how good it is for a cubic model. So I'll go down here to row number 2. And again, let's note that my table headings are X1, Y1. So I'm going to use Y1 and X1 in my tilde equation. Y1 tilde. Okay, A X1 cubed gotta get my letters right here, plus bx1 squared. So plus b, where's my b? There it is, bx1 squared. Plus, see, it's already got a cubic it's building for me, right? It's already beginning to look about how to build a cubic because I started with a cubic here. Plus c x1. Okay, and then plus d. Oops, gotta find my d again. Okay, there we go. So there is the cubic model it built for me. Notice I don't have a need to, there's no log mode box to check that we're all good. We have the r squared value, and it's pretty high, 9769. As we know, it only goes as high as 1, so that's pretty high, and we can see how it's fitting. It's actually fitting pretty well as we look at it. Not bad. Some points are below, a couple points are above, but that's not a bad fit. What I want you to notice here is your A's and your B's, your x cubed coefficient and your x squared coefficient. They have a lot of leading zeros, and in significant digits, these digits here are not significant. So these 4 zeros are not considered to be significant, and these 2 zeros are not considered to be significant. So when it says go to 3 significant digits, we need to put 1, 2, 3, 4 zeros in there and then go to 5, 9, 7. So our significant digits for the constant A is 5, 9, 7. Our 3 significant digits for the constant B is 9, 3, 4. For the constant C, it's 3, 0, and then we would round this to an 8. And then for our D, it's 5.63. We only need 3 significant digits, so we're just going to go with the 5. Any number that's not a 0 is always significant. So 563 would be our constant D. Okay, we'll come back to the graph in just a moment. Let's write that down on our paper and leave yourself a bit of space because we got a lot of zeros to write. Okay, so what is our cubic model? Well, it's y is equal to, and it's a negative 0.1234. Those digits are not significant. And then we have 597, and that's our coefficient of the x cubed term. And then the coefficient of the x squared term, the b, was 2 zeros, which are not significant, and then 934. And there's the x squared. And our coefficient of the c was, our coefficient of the x term, which is c, was a negative, and it's 0.308, and that's the x. And then our d was all significant digits, so we just go to 3 of them, 5, 6, 3. That's 3 significant digits. So 3 significant, 3 significant, 3 significant, and 3 significant digits, and that's our model right there. Okay, so let's use it. Okay, so letter B. Use the model to algebraically predict the number of older workers in 2025. Well, let's first recognize that 2025 minus 1960 is equal to 65, and this is our x value. Okay, so it's 65 years after 1960, and x is the number of years after 1960. So let's use our model. Y is equal to negative 4 zeros, and 4 zeros, not a 4, 597 times 65 cubed plus 2 zeros, 934. I'm right up here, times 65 squared minus 0.308 times 65, and then plus 5.63. This is a calculation. It's a long one, but it's a calculation. We'll pop it in the calculator, and our model is predicting that the number of older workers in 2025 approximately 8.68 million. There you go, according to our model. Okay, let's take a look at a couple more questions. I want to hang on to that piece of paper, I think. All right, let's go to here. Okay, in what year were there 5 million older persons in the workforce? So that's the question where y is 5, and we're going to be solving for x. So negative 0.0000597 x cubed, and then plus 0.00934 x squared, and then minus minus 0.308 times x, and then plus 5.63. We just solve this for x. Well, we're not going to solve cubics algebraically. We're going to use the graphing intersection method. So we're going to have this be a y equals, and we're going to have this whole thing be a y equals, and we want to find the point of intersection. So we're going to use the intersection method. In other words, we're going to focus on using the graph as opposed to algebra here. So let's see here. Let's go back to our Desmos and our graph. And here we are. Let me make sure I get it so you can see it again. Okay, so Desmos already has our equation, our graph is right there. If you'd like to, you can go up here and turn off the points, and that'll just give you the model, which is what we're focusing on. And then we're going to go down to here, and we're going to say, well, there's the model, and we want to equate that to y equals 5 for 5 million people. So y equals 5, and there we go. So it looks like it occurs twice. There were 5 million older persons in the workforce here, 2+ years after 1960, and there were 5 million older persons in the workforce here, 44 years after 1960. So 2.182 and 43.48 is what is graphing these to find the x values. So we'll go back to here, and we'll note, let me get myself together. We'll note that x, it happens twice. In what year? Well, it turns out it happened twice. Okay, so x was 2.182, which is more than 2 years. We're going to make that a 3. It was in the 3rd year, and 3 plus 1960 tells us that in the year 1963, there were 5 million older persons in the workforce. And then we also had a second value in which, because of the dip in the local minimum, and that was in the year 4348. And of course, this is in the 44th year. And we add that to 1960, and the year would be 2004 is when there were 5 million older persons in the workforce. Okay, question number letter D here. Use the graph to find the year within the period from 1960 to 2050 during which the number of older workers is expected to reach its maximum. What is this maximum? Okay, let's take a look. Go back to, let me get myself to landscape mode here. Okay, so we're still looking at the model. And I'll take out the y, I'll get rid of this y equals 5 line there. So between here and here, let's look at our data. So we know that this is between 1960 and this would be between here and here is our time frame. And we have a maximum right there. So let's turn off the points, and we can just touch on our graph. And when we touch on the graph of it, we see it highlights for us the y-intercept. It highlights for us the minimum, the maximum, and the x-intercept, because those are key points. Let's tap here, which is the maximum. And it reaches its maximum 83.805 years after 1960. and that maximum number of workers is 10.305 million. So we want to recognize that that's our maximum and what it means. So let's go back to our paper. Okay, so what's our maximum? Our maximum was, our maximum point took place at 83.805 was the X value, and the Y value was 10.3. And so X equals 83.805, which means, again, that rounds up. We're past 83 years. We're into the 84th year. So 84 plus 1960. We're talking about in the year 2044 is when the older workforce is expected to reach its maximum. And what is that maximum? Well, that maximum is this value, the Y value. That maximum is 10.3 million. So we've interpreted that local maximum, and your teacher here is struggling to spell correctly. There we go. Okay, so that speaks to the local maximum there. All right, letter E. The graph shows a local minimum. Interpret this local minimum in the context of the problem. Okay, let's go back to our graph. Okay, get that back in there. Sure enough, that's our maximum. Here's the local minimum right there. It's already got a gray circle on it, so we can touch it. And that local minimum is 20.5 and 2.73. So the older workforce population, years after 1960, we don't really worry about years before 1960. Looks like it dropped, and then it went up, it peaked, and then it started to show that it's going to be dropping again. We really don't know, but that's kind of the projection we have as the best fit for our model. But here's our local minimum, and let's interpret that. Okay, so back to our paper. Okay, our local minimum is at 20.5, comma, 2.73. Let's interpret it, okay? In the year, we always start out with the X value. So we want to always speak to the X value first. So in the year 1981, how did I get 1981? Well, I took, this is 20.5 years after 1960, which is the 21st year, and I added that to 1960, and I came up with 1981. So in the year 1981, and now we speak to the Y value. So we speak first to the X value in the year 1981. The older workforce, okay, now we need to incorporate minimum or maximum. Was at a minimum of, and now we talk to the Y value, 2.73 million workers. So we want to talk about, we want to include both of these with their labels. 20.5 years after 1960 means we're in 1981. 2.73 million is the number of workers in the workforce, and this is a minimum, so we want to speak to minimum. So we're including the value, the X value, to get us the answer. We're including the word minimum because this is a minimum, and we're including the Y value along with their labels. Okay, so there you have it, working with cubic models.